been a major approach to deal with both the alignment problem in morphologically rich languages and also in a way to cope with the sparsity to learn a better embeddings in neural machine translation. So I will start with a short survey about how this was first proposed and how it worked and how it works with the current approaches and some of the comparisons of different approaches. So the idea of using morphological segmentation was first proposed by Visatza and Federico to use in phrase-based machine translation. So Visatza proposed to apply morphological analyzers and also disambiguation tools because the analysis of a word changes in context, and simply to split each word's features, or let's say these morphological tags, into separate tokens and perform a learn the translation model by mapping the morphological features in Turkish to words in English. And this has worked very successfully because it eases a lot the difficulty of the alignments. So of course, ideally, you would also need such a processor, post-processor in the output if you would need to translate into Turkish to generate the correct inflected forms. But given that if you would have such a tool, it is quite a useful way of coping with this word level sparsity in morphologically rich languages. So shortly after neural machine translation was proposed, we had the problem of dealing with out of vocabulary words, and a major proposal that worked very well in dealing with the data sparsity of unknown words was proposed by Sendrich et al. And the idea of using byte pair encoding as a vocabulary construction algorithm works as if iteratively merging character sequences into subwords based on their corpus frequency. And this has shown to improve the translation accuracy a lot by simply being able to now translate a lot of the rare words, including also loan words, numbers, named entities, any kind of out of vocabulary word you can imagine. So in result of some of my analysis, when I first started working with byte pair encoding, it was to do some analysis, observations on how this would work in Turkish. So one of the first things that I saw, based on the nature of the algorithm, is that depending on, of course, how you choose the hyperparameters, you're going to have a vocabulary that looks quite different than other settings. But in cases of maybe like this, that I have picked a certain number and I look at the vocabulary and I see the repetitions of the same lemma in different forms. So of course, generalization depends on, in such an algorithm, that you observe the same construction in different forms. Like if we have the root is a jail, if we have other words in context in the corpus that have a similar inflections, the algorithm might then be able to capture better the suffixes that are maybe more frequently used. But based on just the corpus frequency, and given the fact that the language itself is very sparse, this results in usually not efficient and compact vocabulary construction that cannot simply be avoided by changing the hyperparameters. This is one of the observations I did by using the byte pair encoding. In the second case, I also did some analysis by looking at the translations. And what I observed is that segmentation, when it happens in the middle of the root, and in cases where it results in a new lemma, such that there is a semantic ambiguity now, so there is a polysemous word, then the word can be translated incorrectly, in the sense that, for instance, in this example, we have the word kanunda, and the root of this word is kanun. But when split at kan is another lemma, which means blood, and instead of in the law, the word is translated as in your blood, which is quite straightforward because the model just learns the meaning of the words by looking at their form and their context, and if the form is wrong, and the meaning will also be wrong. So there is this ambiguity of where to split and how to split becomes important. So something related to generation that I find also crucial is, of course, generation in sequence models is a conditional case, right? So if I have observed a certain sequence in my corpus, then using the subwords that I have split and constructed, I can reuse the words, the subwords, to generate the word form. But if I have not observed the word, and let's say that if I have not observed in this form, depending on what I've observed in the corpus, I might not have the most optimal subwords to be able to reconstruct this word, in the sense that maybe if I have not observed an E as a suffix in another word form, which is actually not very common, and let's say that I haven't observed it. And in English, it is difficult to imagine this, because yes, I might not have gone, but I should have observed done, or any other verb, because the verbs are frequent. But in a language like Turkish, most of these verbs are never going to be observed. There are a lot of cases that a suffix alone is never observed, and because of the vowel harmony, the suffixes change forms, so they might be observed in some cases and not observed in other lemmas, which means that it's just their vowels change, which means that I might not have the subwords to be able to generate that specific form. And falling back to characters, using characters to generate from scratch the word is not going to always work, because then the character level context still suffers from never seeing that word in context or having that meaning, because character embeddings also tend to be very ambiguous. So there is this challenge related to how to find the optimal set of subwords and use it for learning unambiguous embeddings and generate correct translations. So here is the conclusion that I made, some of the observations from the analysis. So the increased ambiguity eventually creates an upper bound on the translation accuracy that we might have from using models that are trained with a byte pair encoding. So of course, the level of how much we can get closer to this upper bound, how much we can avoid this, let's say, inefficiency in the vocabulary, it might depend on the hyperparameter when we are tuning the model, but this tuning is quite costly because it requires training the model from scratch, and looking at the translation accuracy is a very costly process. Okay, so I would like to mention a little bit also about the hybrid approaches, where I have included this study by Huke et al. In 2017. The authors propose a hybrid combination of morphological analysis and BP. So as I might have mentioned before, morphological analyzers, they result in a finite number of let's say, morphemes or subwords that represent the corpus. But there is also a lower bound, because there is only a finite number of morphological features in a word. So they might reduce the sparsity by transforming the words into a sequence of more frequent roots and morpheme sequences. But there is still a finite number of morphemes that will occur in the corpus. And if this finite size of the morpheme vocabulary, the lexicon, is still too large for the neural machine translation model to be practically trained, then there is going to be the need to apply additional vocabulary reduction techniques, like what Hook et al. Did was to apply further byte pair encoding to reduce again the vocabulary size. And they have found that this works better than just using byte pair encoding. So these are just some examples from the German sentences that they had pre-processed. And when they use this for translating from English, they have found it quite useful, because it then eliminates some of the problems that I mentioned before, like overly inefficiently using the vocabulary size and making it more compact by first applying some splitting with compound words or inflected words into smaller parts. It doesn't still avoid splitting the lemmas in the middle, which might still create potential ambiguities, but it just I like this study to show some of the first comparisons of how the two approaches can be combined and how they differ. So at this point, I would like to then devote some time into some research that I did to investigate actually how can this vocabulary reduction be achieved without sacrificing linguistic information, trying to have a notion of morphology while applying segmentation, and in the meantime also having an algorithm that can fit into smaller vocabulary sizes. So the main hypothesis I had in my research was that the morphological structure is inherent to the language, so it is the main generator of the word form that we observe in the data. Thus, trying to model that is going to help generate a compact vocabulary that is also consistent across different collections of data and domains. So in order to test this hypothesis, I have extended this Morphesser-Flatcat algorithm by Brunnerose, and their algorithm uses a hidden Markov model for unsupervised or semi-supervised morphological segmentation. So here in this model, each state or category in the hidden Markov model represents a category of morpheme, such that word formation is modeled as a transition from, let's say, the beginning of the word until observing its root and the end of the word, usually with a suffix. So they have allocated categories in the way that it is coherent with, of course, how in language words are formed. And the probability of these transitions depend on the data are learned from the data. And after learning this segmentation model on some training data, the segmentation model can be used to segment new words, and simply trying to learn a lexicon that can be used for segmentation, we can use the same lexicon for training the neural machine translation model. So the main difference here is compared to, let's say, byte pair encoding or statistical algorithms, the way of splitting works in a reverse direction, such that the words are only split up to bottom approach based on the likelihood of being an actual morpheme. So some of my first results of comparing this approach, linguistically motivated vocabulary reduction with a byte pair encoding, show the on-par performance by as if using two morphological analyzers. So this is actually the graph shows a controlled experiment where let's say that we don't have out of vocabulary words. So the data size is controlled such that the morphological analyzers can cope with the vocabulary size. And when I use this amount of data and compare the unsupervised morphological segmentation and byte pair encoding, I see that the segmentation algorithm, the morphological segmentation algorithm, and the morphological analyzer work on par with each other and much better than the byte pair encoding. And if you look at some translation examples, we see in both cases the ambiguity problem of incorrect translations by byte pair encoding pursues, but with a morphological segmentation, in both cases we can observe correct translations because the ambiguity is resolved by preserving the meaning of the lemma and simply by correctly splitting it, finding the correct root. If we extend the results in the case that we have more larger data and also in different languages, we can see that the improvements persist and that the improvements are dependent on the language typology. So here I have picked 5 languages, each from a different morphological typology. So Arabic is from the templatic morphology, and Czech is mostly fusional and partially agglutinative. German is mostly fusional, but also have some amount of compounding. In Italian is fusional, but still have some complex morphology. And Turkish is mostly agglutinative and still can have some fusional cases. But going from the most sparse to the least sparse would be, the most sparse languages would be Turkish, Arabic, and Czech. And middle to low level of sparsity would be German to English. And we can see that this improvement depends on how much sparsity there is in the data. If you look more closely, what actually is different in the nature of the two segmentation algorithms, we see that the morphological segmentation LMVR reduces the token to type ratio, increases the token to type ratio much in a much larger fashion because it applies a more greedy segmentation. And similarly, in the average sentence length, we still see that the LMVR has a longer sentence length. And in the cases of sparse languages like Turkish and Arabic and Czech, we see that this is actually useful. In the case of German and Italian, what we see is that this over greedy segmentation doesn't have the language because it's already not so sparse, doesn't have so much out of vocabulary words. So it is still benefiting from using byte pair encoding, but the important aspect here is that even if they're overly greeded, the performance is comparable. So in some languages, it is extremely important how the segmentation is applied, and in some cases, it is simply not. So if we compare some main points, how the two algorithms differ, or let's say how two approaches differ, because that is the main idea in my experiments. So in the case of unsupervised morphological segmentation, I have observed the best performance, best improvement is gained in Turkish, where morphological transformations are concatenated. So as the model is more appropriate for learning such transformations, it performs the best. On the other hand, for languages like German, where transformations are fusional, let's say, or Arabic even, so where the transformations are discontinuous, and the segmentation task is not simply defined in the surface level, such that we cannot simply separate the form of the word into two sequences and say this part is a suffix, or this part is this feature, because simply the transformation is not linear. So in such cases, of course, there needs to be more advanced algorithms, or even to me, the task was not defined. It is not possible to achieve segmentation, to separate the meaning, to segment the meaning. So some general conclusions about subword segmentation is that, of course, both algorithms or any other algorithm, so there are many algorithms that follow after this study, and some of them are even better. But in general, these are pre-processing techniques, which means that they have heuristics that need to be tuned, and this tuning is quite expensive and needs to be repeated for new data and new languages. So that is the inefficient aspect of, in general, using subword segmentation. And of course, this nature of the algorithm being applied before machine translation means that the learned vocabulary in any case is not going to be optimal for the machine translation task. So yes, in many cases we can achieve an optimal translation, but an optimal vocabulary, but we don't know is going to be useful for the translation task, and that is another that might create some information loss or inadequacy in optimizing our representations. So in this part of the lecture, I would like to go more in depth into actually how to eliminate subword segmentation by discussing character level models. So character level models rely on internal vocabularies just composed of characters, and by simply learning meanings by composing them in the vector space, so that the word representations do not need to be stored, and that helps a lot with the efficiency. So the first model was proposed by Lingao in 2015, where they proposed using a bidirectional RNN to learn word representations from character representations. So the first time this was tried, it was very computationally costly. So they had to train the word composition model and the translation model separately. And they used the composition model that was pre-trained. Of course, this wasn't very efficient, but they still proposed a very promising approach to be developed in the future. And of course, with the development of better architectures, better computing units, this is now a feasible model to train. Long and Manning the next year improved this approach by suggesting to use the character level model either in the input or the output as the fallback when, let's say, a word is not observed in the vocabulary. So only in the case of out of vocabulary words. And this also helps a lot in the case of unknown, translating unknown words, because at the time, if a word was not in the vocabulary, there was absolutely no way to translate it. And this was a quite useful approach. So in my own research, I also tried, because it was a 2 years fast forward and we already had a better technology, and I decided to try it and compare this to subword segmentation and other approaches. So I implemented an end-to-end character level model, a hierarchical decoder, where each word, instead of a hybrid approach, I went for the full approach where each word in the target is represented as a composition through a composition layer, and the context and attention to the translation task is still maintained at the word level. Only the input and output layers are augmented with character level RNNs to aid the model to learn and to generate especially unknown words.